morning, everybody, and welcome to Foundations of Algorithms. I am so excited to see all of you here today. Can we have a round of applause? What you were just listening to is one of the oldest pieces of computer music. This was generated by a machine, Cyrac, which was actually located at the University of Melbourne, one of the first computers in the world. And the track that you just heard was a reproduction of one of those pieces of music that it played with the sound of the actual computer room. Early computers were not like the laptops you have today or the phones in your pockets. These were giant rooms full of machines, and it took something roughly that size to produce the kind of music that you'd probably hear from an old Nintendo. That piece was in cellar cool, reconstructed just a few years ago for the University of Melbourne. Now, in our class this semester, we have approximately 400 students, and they come from all across the university in different degree programs, different stages throughout their degrees, but regardless, all of you are welcome. We also have our 7 teaching fellows, of whom we have at least one in the room right now, and so I'm going to leave her to introduce herself. Let's wait for that to link. No link, no link. No link. There we go. Taking its time.
I am Casey. I'm one of the teaching fellows. I'm here because I like watching Shannon's theatrics. They're very fun to watch. First time seeing them. This subject's really fun. Make sure you coded classes because we'll have a fun time. And so will you if you come to Shannon's lectures. Hope that's motivating enough to see the fun videos.
So Casey is our head teaching fellow, and along with her we have a team of senior teaching fellows who've been with the class for multiple iterations, as well as some new teaching fellows and our first year fellows that you'll find in the CIS Learning Hub located on level 3 of Melbourne Connect.
Casey!
And so there'll be drop-in help of all different types throughout the semester. There are your workshops, there are of course your lectures, but that takes us to something pretty important. We have our production associate. So this is the person who really makes the show run. That's Rithik over there, who is a graduating student from a Masters of Physics and who's been working with this class for a few years to give you the kind of production setup that you have here. So we do have 2 subject coordinators in the class. There is myself, of course, and over here we have Dr. Han Jiawang. Can we have a warm round of applause for her as well? And she's going to come down to the front. She's going to come down to the front and introduce herself.
Okay, so I think the first lecture is delivered by Dr. Shannon, and I will start delivering the 3rd lecture, and I look forward to the journey.
And tell us a little bit about yourself.
Okay, yeah. I'm Han Zhi, and I started my position in Melbourne University from November last year. So I think I'm as new as to you guys. And this is my first lecture. I mean, the foundation of algorithms will be my first lecture to teach in Melbourne University. And my research interest is in algorithms. So. And the reason for me to start my research is the beauty of algorithms. So I really look forward to also show the beauty of algorithms to you. Yeah, thank you so much.
And as you'll see in the coming weeks, as you write your own code and solve your own problems, what ultimately matters in this course is not so much where you end up relative to your classmates, but where you end up relative to yourself when you began. And it really is all about that delta, whether you've programmed or not, just getting something out of a class like this. And if it does take time, and if you do feel those frustrations, but you simultaneously eventually feel that sense of accomplishment, that just means it's all working. And indeed, hopefully, all the more worthwhile and gratifying ultimately as a result.
The voice you just heard was the voice of Professor David Malan, a Harvard professor. And his teaching philosophy around what the point of being here is something that I want to impress on all of you as well. Because when I was a young student just graduating BCE, he was one of the professors who had the biggest influence on me. And what he says is that it's important to think about it's important to be here to advance your own learning. It's not about the grade you get at the end. Now, of course, we all want to get good grades. But what's more important is the delta, that difference between the day you walk in here, that day today, and where you find yourself at the end of semester. Like I tell people, programming is a skill, algorithms is a skill, and you don't develop skills in a day or a week. Some people are not born piano prodigies, but from a very young age learn to play piano like Mozart. Most of us, however, that's something we struggle through. Some of us a little faster and some of us a little slower. But what determines where we end up is not that initial natural bit of skill. Of course, it helps. What really matters is the dedication and persistence we put in, whether that lasts a month, a year, 10 years, or a lifetime. And of course, computer science is the journey of a lifetime, and I hope one that you're really beginning to start today. So what are we doing in this specific class? This class is different from perhaps other programming classes you've done before, in that the thing that we care deeply about here is not the programming itself. It's about the art of problem solving and what understanding problems can teach us about the way the universe is constructed. So we'll uncover deep links between the nature of physics, the nature of mathematics, and of course, the computers that we actually solve some of these problems on. But remember, these computers that we're actually running the algorithms on at the end of the day, they're only one representation of solving the problem. If you had enough time, you could, by hand, do the same steps that the computer does to solve the problem. So what we care about in this class is this pattern of problem solving, is the steps we use to solve the problems, and not the particular machine that we're instantiating it on at the end of the day. So fundamentally, algorithms are about this picture. If you take nothing away from the entire semester, this is one of the most important things to take away. And you'll see here, I have a little duck in the corner to indicate that I have borrowed with permission some of the materials from David Malan and CS50, where I've actually taught a little previously. So keep an eye out for that duck, and there will be some duck merchandise giveaway throughout the semester as well. So our picture here is one of transformation of input to output. And that black box, does anyone know what we'd call that black box, KJ? A function, one word? Oscar?
Computer?
It's in the name of the subject. Algorithm, that's essentially what this thing is. It's this process that transforms a given type of input into output. And this is what we're going to be studying for the semester. Algorithms, this big black box that can transform a given set of input into a type of structured output. Now, one of the things that you might think about is, why do we bother with this process? If you give me a problem, I already know how to solve it. If you give me a deck of cards and tell me to find the ace of spades, I can lay them out on the ground and find the ace of spades. This is really the answer. Our universe is sadly finite. Our lives are finite. The tasks we have to do need to be done by certain deadlines. If we had infinite time, this challenge of solving problems wouldn't really be such a problem. Just try every possibility and pick the one that's the right answer. And at the end of the universe, maybe you'd picked it. But like everything, our time is finite. And so this is what actually motivates our study here. We've got to find ways to do things efficiently within the bounds of the context that we have. So in some contexts, you'll need a problem solved in a day. In another context, the problem needs to be solved in a month. In another context, the problem needs to be solved right now as soon as you can get it. And in each of those, understanding what the actual needs are is going to determine what kind of algorithm you need. And part of our quest is going to always be, can we do better? So we've come up with an algorithm that can solve our problem in a month. Can we come up with an algorithm that can solve the problem in a day? What about a week? What about as soon as I hit the enter button? So another reason why we're going to care about context a lot is that the actual machines that we're using to do the programming are changing all the time. They're changing in speed. And we want to have some way of describing the problems themselves that doesn't actually matter whether you're using the latest MacBook Pro released yesterday or the day before, or you're using one of these Macs released in the 1980s. Now, obviously, these Macs are a lot less capable, but the types of problems they can solve are fundamentally the same ones. It would just take a really long time for one of these 1980s Macs to do some of the tasks that we do on our modern computers. But when we characterize an algorithm, we don't want to have to ask every person, what particular computer are you running? What year was it made? We want to be able to say, well, this is how many steps the problem takes to finish. And given that your computer can do this many steps per second, here's an estimate of how long the problem will actually take you to solve. Oh, Does anyone know what this machine is? Anyone have an idea? Someone who hasn't been in... Oscar, you've already answered a question. I need someone new and someone who isn't from FOA last year. Hanja, you're also not allowed. Someone else. Yeah.
I forgot the name of it, but like the codebreaking.
And what was your name?
Annie.
Annie? Yeah, Annie's 95% of the way there. This is a code machine, but instead of breaking codes, this is a machine that makes codes. And when I say codes here, I don't mean like computer programming code. I mean like secret spy code. And that's actually my area of research, is figuring out how to encipher messages and decipher messages. So this particular machine is called the Enigma machine, or it's one of a series of Enigma machines that were built, primarily used by the Nazis during World War II to hide messages from the Western powers so that they could conduct their war effort. And this is going to be the topic of the remainder of the first chunk of our lecture. We're going to discuss, okay, so if you get an encrypted message from the Enigma machine, what are some of the tasks you might need to do to crack the code, and how quickly can that be done? And this is a particularly salient problem for us to start the semester with, because it was one of the very first tasks for which computers were actually used. Now, I do have to confess that the particular algorithm we're going to learn in class today is not the same one that was actually used to crack the Enigma code, but it's still going to be instructive and help us understand this kind of process. And in fact, I will post after lecture some really interesting history that you can read, very accessible, about the Enigma cipher and how and what led to its breaking by the Western Allies.
In post-World War I Europe, secrecy between paranoid nations becomes paramount. The growth of international commerce creates a need for companies to keep their information secret from competitors. Germany's Arthur Scherbius develops the Enigma machine as a means of keeping those business transactions secure. It works by generating an electric current when a letter key is pressed. A number of moving mechanical parts then scramble the path of the current, producing a different letter each time the key is pressed. The Enigma machine is about to become the German Army's most powerful code-making weapon in World War II.
But we over here are the brave Allied powers, and our goal is going to be to crack the Enigma cipher. So how do we go about breaking a code? Well, one of the main techniques that was used historically with codes, at least prior to, say, the 1950s, was to look for patterns in the enciphered output. And perhaps if you can find patterns, perhaps that map to some form of statistics, you can go backwards and figure out, okay, what was the plain English text or the plain text or the German text, whatever it happened to be, what was the original text that originally produced this statistically distinct output? So here is an example of our ciphertext. And now what we want to do is to try and find some statistical patterns in it that we can then use to go back and recover the plain text. So let's boil this down to a much more concrete mathematical style problem. And here's one of the patterns that we might look for. how can we find repeated sets of letters? Because repeated sets of letters in the code might indicate to us repeated sets of letters in the original message. So for example, if the Nazis are using the word Heil a lot, like they might do at the end of a message, then if we can find series of letters that always seem to appear right at the end of the message, perhaps those are a clue as to what it was in the original thing. If we know that those original letters were Heil, that will give us what we call a crib, a set of known letters that we can then use to break the rest of the code. But we're in the middle of a fierce war, and so it's not enough to just find these patterns and break the code. We have to do it quickly enough to save the Allied soldiers and save the people who are being persecuted in Europe. So how quickly and efficiently can we find a repeated set of characters, a repeated set of L characters? So this means if the repeat is 4 letters long, L would be 4 in this case. So here is an example of a sequence. fat.rat.eat.bat.cat.eat.fat.rat. Can anyone see a pattern of letters in this one? Are there any repeated sets of letters? What was your name? Yeah. Okay, can we see any repeated letters in here?
80 dots.
Oh, we see 80 dot. Are there any longer repeats that appear? I think I see eat. Eat seems to repeat. The word eat, E-A-T, is there, eat dot, and then there's eat dot. So we're good. There are a number of different repeats in here. Here we have our parameter m, which says look for repeats of at least 7 letters in length. So let's see what happens when we run this. And I have written a program ahead of time called find repeats 0. And into find repeats 0, I'm going to send it a file, give it some input called text1.txt. And let's actually run this on my real computer instead of just doing the demo that way. So here I've brought up my trusty computer over here, and I'm going to enter some commands into what we call the terminal. Now the terminal is just a fancy way of saying there is a program running somewhere on the computer which understands certain commands and is set up so that you can type things in and it runs the commands that it understands. And so this is my terminal here. There are lots of different terminal programs you can use. In this case, this is a terminal that is built into a tool called VS Code that we're going to use throughout the semester. So I am going to navigate to a directory called live where I have our demos for today. And we'll talk about some of the commands used to do that later. And I'm going to run find repeats 0 of length 7 with test1.txt. And if everything is good, there we go. The program produces the following output. Now, it might be a little hard to see because our projector is not as awesome as it could be, but here is our output. We have a string of length 32, and a string is just a fancy computer word speak of saying a sequence of characters, of letters, of numbers, of symbols. So we have a string of 32 in length. We were looking for repeats of at least 7 in length, and we found 3 of them. Fat.rat, at.rat. and at.eat. Those are our repeats. So that seemed to run pretty quickly. I think we're probably done for the day. It was lovely seeing you all. No? Okay, what am I missing here? My program seems fine. What am I not thinking about? Anyone have ideas? Why are we not done for the day?
Because you can't apply it to different situations.
Okay, getting close. What was your name? Caitlin. So Caitlin's kind of like pointing us in the right direction here. This worked very well for a very small string and for a very small number of letters. But we're up against the Nazis, and they are sending codes by the hundreds every day that are really long. And we want to know if our programs are actually going to work when the task gets a little bigger. So let's run this, except now instead of test.txt, I'm going to give it the text of War and Peace. Anyone here read War and Peace? Anyone here looked at War and Peace, the book? Okay, KJ, how many pages is War and Peace? Yeah, It is a big book. So we're going to start with a nice chunky text size and see what happens when we run our same program on warandpeace.txt. And in fact, I'm going to open up warandpeace.txt so you can see it. Here we are, warandpeace.txt. Computer is loading it because it is a big book. There we go. Author Leo Tolstoy. And here we have the entire text of War and Peace. It's going to take me a long time to scroll down. Everyone had enough? Someone want to go to a particular chapter? No? No favorite chapters? Okay. Enough War and Peace. Let's give it a run. Okay, I will see you all in like 30 minutes. I'm going to go take a bit of a break. Okay, now what's wrong with our program? What's the problem here?
Too slow.
Too slow, yeah. We've got our problem, and if we want to actually crack the code and defeat the Nazis, we're going to need to go a lot faster than this. So let's take a look at what we were actually doing in our program, in find repeats 0. So this is what we call an algorithm. Now, I'm kind of like being a little fudgy here because the algorithm isn't the English words on the page. It also isn't the program that I've written. The algorithm is something more abstract. It's the idea of the steps that we're doing. And so you can say this is the algorithm. You could also say the code is the algorithm. And you could say if you were manually looking through it and following these steps, you could say what I'm doing is the algorithm. What we're really focusing on here is the abstract version. What are the set of steps that we're doing? And you can write that in any programming language you want. You can write it in plain English in a bunch of sentences, or you can write it in code. And so that's an important thing to remember, is that the algorithm is really this more abstract, beautiful set of steps that we're performing here. But let's go into our actual set of steps that we're doing for find repeats. And this is our process. So read the sequence S, and for I equals 0 up to n minus m, do the following. Now, hopefully all of you have seen at least a little programming before, or you wouldn't be in this class. If you have problems with that, come chat to me after. But we're going to do a loop. So starting from the value I equals 0 to I equals n plus m, do. Okay, but then we've got another loop inside that loop. Okay, for j equals I plus 1 to n minus m, do. Compare m characters starting at si and sj. If all m characters are the same, then write an output line. Now, that sounds kind of abstract and hard to follow. Me just repeating that probably didn't do very much for you. So what do you think, how do you think we should try and understand this? What would be a reasonable next step? If you were trying to understand this for homework, what would you do? Run it on a small test case. And when you say run it, what do you mean?
I mean, like just by hand.
By hand. That is a great idea. What's your name? Tom. Tom. Great. Okay, so Tom's going to help me out and we're going to run this by hand.
Okay, so we repeat the first thing. So we take the...
So very first thing is...
We read the sequence.
Okay, read the sequence. Let's assume we've done that.
Then in our outer loop, we initially have I equals 0 and j equals 1.
Yep. So then let's write this as I and j. Our j is at position 1.
And then we take I, so the I is the F, the j is the A. And if they're the same, we write the output line. So we write FA.
Are I and j the same?
No.
Okay, so I guess we don't do that then.
And then we go to the next one. So then we go F and...
So slow down a little, go through our steps. So compare all the characters starting at SI and SJ. Okay, that didn't work. But what we haven't really done is compared all the characters. We kind of skipped that step right out. We glossed over it. So how do we do that?
We go to the next...
So let's, still skipping steps, let's say our m was 7. And so we have to compare 7 characters starting at F and starting at A. So let's check 1, 2, 3, 4, 5, 6, 7, fat.rat. And let's start 7 characters starting at j. 1, 2, 3, 4, 5, 6, 7. So we've compared fat.rat. To at.rat. Wait, 1, 2, 3, 4, 5, 6, 7. We've compared fat.rat to at.rat. Now we're ready. They don't match, and so what do?
We iterate j by 1 and then check.
Okay, move j along by 1. Now what do?
We look at the I again, so that's fat.rat.
Okay, fat.rat, and what do we compare it with?
The t.rat.e.
t.rat.e. Are they the same?
No.
Okay.
Iterate again, check, same for I, and then dot rat dot ea, the j.
And I'm getting a bit tired of this process. Something about it seems pretty inefficient. Can you think of one way that we could improve this process?
If you could check just the first character initially.
Yeah, so explain the intuition there.
Well, because instead of comparing the first 7 characters, if you just compare the first character on each, you can do it faster and you don't have to compare the entire word. And if they don't match, you can move on to the next one. If they do match, then you can check the wider string.
So being super explicit about our intuition there, for 2 strings to match, they must necessarily match in that first position. If they don't match in the first position, there is no possibility that they match across all the positions. Then we know, well, if we've already decided that they did match in the first position, then we can check the next position along. They must necessarily match at the second position if they're going to match for all the characters as well. And so this gives us an optimization. What we can do is, instead of comparing all the characters, we can compare up until... When do we compare up until? Anyone else an idea? Oh God, a hand over there at the back. Let's pass the microphone back. When do we stop?
We stop when there's a difference.
Yeah, so at the first place where we notice a difference between our string starting at I and our string starting at j, we don't need to compare anymore. Because if we know they don't match at position 3, then there's no way that they match at all 7 positions. And so that allows us to improve our algorithm and actually get a huge performance speed up. Now let's see what that actually looks like here. I'm going to take us over here. Actually, go here, and I'm now going to run a version of our algorithm called find repeats 1. And here we go. Now we're running find repeats 1, and you can see how much faster that is going through all of War and Peace. And if we leave it for a little while, it will finish. Still a bit slower than we'd like, but it is going fairly fast. Now, one extra thing I will say is one reason why it's going slowly is because we're printing so many things to the screen at once. We're trying to display so many lines, and that actually slows down the process. If you want your program to be fast, you should only display the things you want to at the end rather than as you go, and that will save you time as you iterate through. So this comparison of the 2 different versions of find repeats takes us to a more fundamental question, which is, how do we actually compare these algorithms? So we know that number 1 was better than number 0, we've saved some work, but how do we characterize that amount of work saved? And why should we care? Why don't we just get a faster computer? So this leads us to the next little chunk of the lecture, where we're going to actually talk a little bit about different ways of characterizing how much time an algorithm takes relative to how much information we're giving it, the size of the problem. The bigger the problem, the longer the algorithm is going to take. But if we're comparing 2 different algorithms, maybe one of those algorithms will grow in the amount of time it takes more slowly than the other as we slowly increase the size of the problem. So let's try and graph this out. That seems to be a good way for handling these sorts of problems. And we're going to essentially ask the question in this form. If we grow our problem size or our input size by n units, how many units will the amount of time that the algorithm takes grow by as well? And we could ask this about the time, but we could also ask this about the memory that it takes for an algorithm to run successfully. And this is what Hanja's work is actually all about. As a theoretical computer scientist, she spends a lot of time considering kind of the tension between making things run faster and consuming more memory on the computer. And I'm sure you'll hear a lot about that through the rest of semester, and I'm very excited to hear about it. So this takes us to a form of notation that we're going to use throughout the semester to kind of describe this pattern of growth. And this is informally called big O notation, and the field of mathematics that's dedicated to discovering the big O version for different algorithms is called asymptotic analysis. Because we want to know, as we go further and further along the axis of growth, how do they start behaving in the long run? We don't really care if it takes a bit of time to start running at the beginning. What we care about is, okay, once we've got the thing set up, how long does it take proportional to the size of the growth in our input space, in our input? So we can make this pretty easy to understand graph, where the x-axis is the size of the problem, and the y-axis is the amount of time it takes us to solve the problem. So you could imagine that two different points on the size of the problem axis might be our little fat.rat string is one close to 0, and War and Peace is a little further along as a bigger problem. Okay, so let's graph an algorithm. Doesn't really matter what one this one is, but this is an algorithm that for every n units that we increase the size of the problem, the amount of time it takes to solve it also grows n units. Now, one thing that I'm kind of covering up here is that there might be different slopes associated with this. So it could be an n on 2 growth in the size of the time relative to the growth in the input space. One of the things that asymptotic analysis actually does, and we'll talk a lot more about this in week 3, asymptotic analysis generally throws out these factors. So that 1/2 in front of the n over there, when computer scientists typically talk about asymptotic analysis, that might actually go out the window. What we want to care about really is the proportional growth, and we'll talk more about that soon. So we can see here, for any given particular size of problem that we pick, we can estimate its change, how that will impact the change on the running time. And in this case, you can see that the problem where the time grows proportional to n, rather than n on 2, takes longer for the same size of input. So we pick a specific point on our graph at the size of the problem, and for the n on 2, the height of the line, the height of the point on the line, on the n on 2 line, is lower down than on the n, which means the n on 2 version is faster for the same problem size, but also we can see this for any size of problem. That pattern is going to continue. Now, here's a different algorithm. This one runs in log n time, and that's a colloquial way of saying for every n units of growth in the problem size, the amount of time that it takes us to solve the problem is only going to grow proportional to the log of the increase in the problem size over here. And we could do this for all different kinds of growth rates. You could have n squared, you could have n cubed, you could have n factorial, and that's going to be some of our discussion throughout the semester is how do we pick algorithms, or how do we make algorithms, or how do we come up with algorithms that do better and better such that we can go from like an n squared algorithm that grows really, really quickly to maybe an algorithm that runs in linear time, so proportional to n, or even to one that grows in log n time. That would be really nice. So another way of doing our analysis that Tom did for us before, where we were trying to figure out how long our algorithm took, is we can look at the written description of the algorithm and try and figure out concretely what is going on that is taking a lot of time. And if we look up at our algorithm here, we can see right off there's a double loop, so we have 2 loops. And then inside the double loop, we have something that also seems to take a bunch of steps. So this compare m characters here, that's going to take at least m steps if we're going to compare m things. And this is happening over and over and over and over again. So one way that we like to do our algorithmic analysis is actually to do this process, which is to write it out, label the different parts of the program, say how long each part of the program is going to run, and then add them up together. And this is going to be a task that you will do throughout the semester when analyzing your own code. So what we can do is we can look at our loops that we just did and actually count how many times they're going to run. So let's go back here. The first loop, how many times the outer loop, the top there, starting at line 2, how many times is that going to run? I've already heard from you, Tom, so I need someone new. N minus m times? Who did I hear that from louder? Someone's voice was now nice and loud.
N minus m's value then squared.
So the outer loop does run n minus m times because it goes from 0 to n minus m. But, you know, if n is War and Peace has a lot of letters in it, and m was like 7, so we probably don't really care about the 7 particularly. So we can essentially say, for like being lazy computer scientists, let's just call it n. Let's say the outer loop runs in n times. What about the inner loop? Also n minus m? So we can probably do the same thing again, right? N is really big, m is kind of small. So that's really n squared. For every time the outer loop runs, we do the inner loop n times. The outer one runs n times, which means for each of those n, we do n. Another way of saying that, if you're in university and not in high school, is that's just n multiplied by n, which is n squared. Now, in the inner loop, we then want to count up how much work we're doing. So let's count. Okay, compare m characters, and I said how many steps that should take to compare m characters. What did I say? Just to compare m characters, if I tell you you have m letters on this thing and m letters on this thing, how many steps is it going to take me to compare each of the m letters in both of them? Well, it's not going to be m squared because I don't have to check all the letters for each one on this. I can just go, okay, is the first letter the same? Is the second letter the same? Is the third letter the same? Up to m letters. So more or less m. I mean, maybe 2m if you're saying, well, you have to move this one along one and you have to move that one along one. But we're computer scientists, we're not going to care about that too, just like we're not going to care about the n minus m being like a difference of 7 there. So we have work m in the middle. So we have n on the outside, n at the second layer, and m in the third layer, n, m. And let's multiply that all through together, and what do we get? What do we get? N squared m. So the algorithm is going to take n squared m character comparisons to run. And you'll notice here that I've said character comparisons. That's one useful way of thinking about the total number of steps of the algorithm, because we don't know inside the computer exactly how many steps each bit of the process is going to take, so counting the number of comparisons seems a reasonable proxy, and then there'll be some fudge factor that we have to throw in. So what I actually did is I went behind the scenes to figure out for the computer, how many steps does a character comparison actually take? How many steps are inside the loop? And when I looked at the deep in machine code, I found roughly these 10 steps. And you can actually do this with any program. You can run a command on the computer and it will show you the instructions that the machine is running at a much lower level. This is called assembly language. And when you normally write a computer program, it's going to get converted into this kind of like special machine instructions after. And if you're in the more comfortable class for tutorials, you'll probably learn a little bit of assembly language this semester. So let's do some basic computation here. Let's say that n is 1,000, so we want to run this on an 1,000 letter string, so not quite War and Peace, but also not our fat dot rat dot. Let's set m equals to 10 just for convenience, because we can multiply numbers, round numbers in base 10 pretty easily. Then n squared m gives us 10 to the 7. But remember, that's 10 to the 7 character comparisons, but because each character comparison takes 10 assembly instruction steps, that's going to give us an extra power of 10 there. So 10 to the 8. My laptop, this particular laptop, can do about 10 to the 10 things per second, or instructions per second. So this gives us about 10 milliseconds to run this program, which, I don't know, that's pretty good. That's faster than I can kind of tell. So if I press the enter key, that will, for all intents and purposes, look instant to me. But let's make the problem size a bit bigger. Suddenly, we have 1,000,000 letters, and the length of repeat that I'm looking for now is 100. Let's recompute this. 10 times n squared m, and what do I get? 10 to the 15 on 10 to the 10. That's about 30 hours of work for my laptop. So as soon as we start to scale the problem, we run into issues. Okay, so this is what I mentioned before. You might say, well, Shannon, you only spent 7 grand on that computer. Why don't you spend 30 grand and then your problem will be done quickly? Well, other than the fact that I don't have 30 grand sitting around for a laptop, we'll do a collection at the end of class if you want. If you think this is the best solution, we'll collect 30 grand together and we'll defeat the Nazis with a faster MacBook. But I might suggest that relying on faster computers is probably not the best solution here, even accounting for the fact that computers get a lot faster really quickly over time. Does anyone know what Moore's law is roughly? Doesn't have to be the exact statement of it. Got a hand right in the back. Where's the microphone? The microphone is over here. Let's pass it over. Lily, okay, what is Moore's law?
That roughly year over year, the system gets about twice as powerful.
So not quite year over year, but you nearly got there. It's roughly 18 months was something closer to the original statement. So every 2 years-ish, would expect to get a doubling. Now, do you know anything about Moore's law today?
It's been dead for a while.
It's been dead for how long? How long has Moore's law been dead for?
Not quite sure, but it's been a while.
It's been a while. It's about 10 years. So when I started playing with computers as a kid, in my dad's office, Moore's law was still very much alive. Every 2 years, I would look forward to a new toy that would run twice as fast, but that no longer happens. And so this seems probably a bad thing for us to rely on if we're using that to defeat the Nazis. We don't have enough time to wait around for that. Okay. Moore's law is dead. So even with Moore's law, let's assume it's not dead, but even with Moore's law, we would have to wait 20 years for our algorithm on the bigger problem size to get as fast as our algorithm on the small problem size. So if Moore's law is alive, if Moore's law is dead, if we have 30 grand to buy a faster computer, we're still not solving the problem. The way that we should solve these problems is with algorithmic design and analysis like we did before with Tom, where we found, we could actually get a little bit of a speed up here if we didn't compare all 7 characters every single time. So let's cross that out. On average, we can do much better. Now, this is actually something that I elided in our discussion before. If every time that you ran the algorithm, you were getting a match, you actually would still compare 7 characters every time, because you say that match, 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 great. Next one. Match, 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 match. Next one. Match, 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 match. Next one. But on average, we know that in most cases, we're not going to get matches. Most of the time, the first letter and the first letter is not going to match. If they were random strings, how often would we expect the first letter to match, assuming all lowercase letters and English alphabet? 1 in 26 times. So let's say you pick any letter from English from A to Z. There are 26 of them. So let's say we pick F, and the next letter is picked randomly as well. There is a 1 in 26 chance that you pick another letter F as your starting thing. Now, we know that actual texts in the real world are not random like that, so I would probably expect it to be a little worse of an improvement than 1 on 26 times, but still do pretty well. So here is our new algorithm that was proposed by, remind me your name? Zayad, that's right. This is the new algorithm that Zayad proposed, which is swap out the line comparing all characters, stop as soon as you notice any discrepancy. This was much faster in practice. But let's take a look at the algorithm. We still have a problem, which is that even though our average case is better, if we do our analysis as before, okay, outer loop runs n times, inner loop runs n times, middle one in the worst case still runs m times, n by m, that still gives us n squared m. So we haven't gotten really the improvement that we wanted. So our next step is going to be to ask the question, okay, practically on average we can do much better now. Is there a way that we can do asymptotically better, such that our worst case is actually improved? Now, if the answer was no, we could probably end class here for the day and go home, and we'd just say, okay, whenever you have a problem, just improve the average case. But fortunately, we are going to have ways to improve our algorithms, and this one is going to be instructive because I'm going to show you 4 different ways that we can improve our algorithm that'll help you think about some of the issues that you can work through when attempting to improve one. Okay, so let's redo our analysis, factoring in the average case. So when n is 1,000,000, we're still going to need to do at least 10 to the 12 comparisons. That's still 1,000 seconds. So now here's the reveal. It's still running. So faster, still not fast enough. And this really, for me, is your welcome to computer science. Many of you have done programming before, but the thing that makes computer science different and makes it a science is that what we're concerned about is not necessarily how do we build a slightly faster computer. What we care about is the fundamental structure of computation. And in particular, this leads to the field of theoretical computer science, where yes, you implement the algorithms and that's important, but what we really care about is the links between the structure of the universe, the nature of the problems, and what we can design to make things efficient. So now we're going to take a few minutes break. Looking forward to seeing all of you in a couple of minutes. And welcome back, everyone. Glad to see that all of you made it here after the break. So last when we left off, we were talking about what it means to think about computer science. And one of the key concepts that you're going to encounter in this course, as well as throughout your computer science education, is the notion of a space and time trade-off. Now, please forgive the space-time pun here, but the idea here is in many instances, you'll be able to make your algorithms faster at the cost of using a bit more of your computer's memory. Now, that seems a little counterintuitive. How can putting more stuff inside the computer make my algorithm faster? And the answer to this question is part of the journey that we are going to take through the rest of the semester, understanding the part of the course that talks about data structures, ways of arranging information such that they actually make some of our steps more efficient. Now, data structures are an abstraction. Just like the notion of an algorithm, a data structure isn't a physical thing like a filing cabinet, or if you were to peek inside your computer's hard drive, you wouldn't see a data structure there. It's more a way of abstractly organizing the information such that when we then need to access it later, we can do it very efficiently. Now, there is a link to the physical world here, which is the way you store your data structure inside the computer's physical memory will also make a difference. And depending on the particular construction of the processor of your computer and the memory of your computer and what we call the memory hierarchy of your computer will make a difference to which of these structures are the right fit to solve your algorithmic problem. And also, of course, once again, depending on our problem size. One example of a data structure that all of you are familiar with still is files in folders. Now, if we open up the computer, I don't see any folders in there, that didn't work. But nonetheless, all of you are still used to this abstraction, this notion that within the computer, within your computer's hard drive, there are actually these folders. And these allow us humans to navigate efficiently through the file system of the computer. You can imagine lots of different ways of arranging things. It could have just been every single file that you want on your computer is labeled with the numbers 1 to 100,000, and you've just got to remember which file you want. But instead, we have a data structure, this abstraction, that we then present to the user that allows us to do things like find our documents much more quickly. So just in the way that we have data structures that are useful for humans to more efficiently access things around our computer and run our algorithms, there are also going to be data structures that are useful for computers to run the algorithms that the computers are running internally. Now, the challenge here is going to be to pick the right combination of algorithm and the right data structure to go along with it that suits the particular problem that we're facing. And this is true of not just our code-breaking problem that we've got for today, but for most of the problems that we're going to see this semester. Now, let's go to our fat.rat example and show you our first more complicated data structure. So here is what we call a suffix-array. And the way it is constructed is by taking a string, in this case our fat.rat.string, and then cutting off one letter at a time and putting those in a big table. So in the first line we have our full string. In the second line it's the string missing the letter F. In the third line it's missing the letter A, and so on and so forth. What I've done is, starting with this one at index 1 just for today, I've arranged all of them. But what we could do is also arrange things in a different order. So let's keep the numbers associated with each line, but now what I'm going to do is I'm going to arrange the entries in this table in what we call lexicographic order. Now, lex comes from the Latin for letter, lex. Lexicographic comes from the Latin lex for letter, and so this means in kind of like alphabetical order, except lexicographic for computer scientists is often taken to include symbols and numbers as well. So let's do that, and I'm going to transform this magically for the time being. We'll talk about how to do this transformation of sorting it later in semester. But for now, you'll see now things are in lexicographically sorted order, where the string at the very top is the first, like A, and then the one at the bottom is Z or Z. But in this case, because we have a symbol, I'm going to put symbols after Z in my lexicographic order. So at the top, I have at, then at dot bat dot cat dot, and then at dot cat dot eat, etc., etc. Now, I'm going to take us back for a second. Why are we doing this? What was our task? What was something about Nazis? What were we trying to do?
Match substrings.
Match substrings. We were a bit more than matching substrings. We're trying to look for, it was along those lines. What were we trying to do?
Trying to find the sequence.
Looking for a certain type of sequence. Do you remember? Not code. Looking for repeated strings. Now take a look at this. Can you see anything interesting about the way that repeating strings are arranged? Or repeating substrings? Anyone see a pattern here? So let's say we are looking for 2-letter repeats. Let's pick one row and look at the row above it and below it. So let's look at the row labeled 6. And let's say we're looking for repeats of length 2. Oscar, we're just about ready to give it away, so I will let you... Do you know what's going on?
To get lengths, the same substring of length 2, you can just look at the adjacent lines.
And... Sorry, say that one more time a bit louder.
You can look at the adjacent lines to get the substrings because they've already been sorted.
Yeah, and so this sorting that we've just done means that everything is now arranged in such a way that if there are repeated substrings, they're actually going to be next to each other in our array. So now all we need to do to find all the repeats is just go from top to bottom and look at the adjacent rows to see, look at consecutive rows to see, are we still getting that matching pair? So if we want to find all the places where at is repeated, let's go down, let's start at the top, and then we can get down up until there are like 7 or 8 entries that all start with at dot. And then we have a few that don't match, like bat.cat, the one adjacent to it, doesn't have a matching substring for BA. What about starting with C? No, cat. The next adjacent to cat, there's no matching one. But when we get to eat after that, you'll see there are there is a pair of matches for each. And just by going down this table, we can now find all instances where there are repeats of 2 letters. And this is, in theory, really efficient once you've gotten to this point. So looking at our data structure, we have a few key properties that made this work. So the first property that made it work is this sorting, the lexicographic sorting that we have. The next is that every possible suffix in our string is present there. So I've taken all the suffixes, not just a subset of them. Each suffix is matched to its starting index, so where in the string it appears, which allows us to easily report back to the user where that substring match is. And then the strings, this is the final property that Oscar pointed out, that the strings most similar to any suffix are on either side of it. So as Oscar said, the way we can check for repeated substrings is by doing a process where we set this up and then just go through it. So here is a pseudocode version of that algorithm. So I'll give you a second to look at it. And this is just the process that we were doing before. So the very first 2, after we've read in the sequence, the first 2 lines there are putting all the suffixes into our data structure. And in this case, let's just call it an array for the time being. So for I up to n minus m, start the string at position I and put that into our array. Now you'll notice here that I'm not actually copying the entire string in. What I'm just copying is the index of it in, and we can use that later. Then sort that array of indices based on the substrings that start at that index. So let's go back a slide for a second. It's the unsorted one. We're constructing this left-handed column with all the numbers from 1 to 31. And then the next bit of our algorithm is arranging those numbers 1 to 31 based on what that second column should be in terms of sorting. So that's what the algorithm's actually saying there. So sort your list of numbers based on the substrings that refer to those starting indices. And then from I equals 0 to n minus m, which is just the size of the table, compare it most m characters starting within our right column. And so that's our S array there. Same thing as before. If there's no difference found, then write an output line. That means the 2 substrings actually match. Now, one thing that we didn't discuss earlier is why we're only going to n minus m instead of n. Does anyone know why? Already heard from you guys. Why do we go from 0 to n minus m? Yes, let me run you up a microphone.
Yes, and it's because we check m characters in front of the position. So if you were to go past n minus m, it would go out of bounds.
That's perfectly right. So let's say we're looking for repeats of at minimum 7 characters in length, and we're looking at the second last character as the starting point. There are not 7 more characters to check. So it's impossible for there to be a substring of length 7 starting at the second last character of the string, because there just aren't more characters. So that's why we're only going to n minus m. Thanks very much, Amir. So now, what is the running time of this algorithm? This is a bit of a trickier question, but I will give you a hint that sorting k items in this instance is going to take on average k log k, where k is the number of items that we have to sort. So there is the algorithm, and sorting takes k log k. I'll give you a second. Okay, now we're going to play a bit of a game. So here are a few options. If you think it's going to take time proportional to n, hands on head. If you think it's going to take time proportional to n squared, or n squared m, either of those two, hands out in front. And then if you think it's going to take n log n, stand up. So n squared m, stand up for n log n. Okay, so who had their hands out? With their hands out. Okay, Tom, you have your hands out? This is n squared m. Why do you think n squared m?
Because in the worst case scenario, it's going to be sorting slower. Because if it's completely out of order, you have to iterate over everything twice. You have to have two loops that repeat n times to sort everything ideally. So then you have to have a n squared in there, and then m for the number of times it takes to do the character comparison.
Okay, one answer. Other answers? Who said proportional to n? Annie, you said proportional to n?
I mean, like, the sorting thing makes sense, but like that depends on what sorting algorithm you're actually using.
Okay, depends what sorting algorithm you're actually using. Here, let's give you a microphone.
Since we already defined the average time for like sorting it as n log n, so I'm just gonna assume that like the sorting algorithm we are using has an average time of n log n.
Yep, that's fair enough. But you had you said proportional to n.
Oh wait, no.
N log n was standing.
Okay, no, it should be n log n then, because like n log n is like larger than n, so like the time is based on the sorting.
So let's go through our algorithm bit by bit and actually see how much each chunk of it takes. So we've got a for loop that goes from 0 to n minus m. Out loud, how many times should this run? N times, because we don't care about the m really, because the m was small and the n was war and peace. So that part at the start takes n time. So if we were to write it down, are there whiteboard markers anywhere? No. Oh, we've got one. We'll write it down here. I was about to write on the wall. We have n for the first chunk. Okay, next chunk, sort. How long did we say our sort took? N log n, so that's n plus n log n. And for those of you who are paying close attention, you'll notice that I am fudging something a little because the sorting is sorting entire strings. So bit of inaccuracy there, but we'll ignore it for the time being. And then how long does our second loop take? So the outer loop is a maximum of n steps, but how many instructions are there inside? So compare at most m characters. M. Okay. So now let's times by m. Now what do we say about m? Is it big or small? Small. Okay, so which of these terms is going to be the biggest? So this is n1 times n. This is n times log n. And this is like n times, I don't know, 7. Which of these is going to be the biggest? This one is probably going to be the biggest as soon as n starts getting large. Like if n is 1, then it doesn't really matter, and n times 7 is going to be the biggest. But as soon as n gets big, log n, even though it grows slowish, is still going to grow. So you could get something like n plus, I don't know, 1,000 n plus, 1,000 plus 1,000 by log of 1,000, which I don't know what that is. 100, what's log of 1,000? Yeah.
I think it's around
10? Yeah, I think that's about right. So that would be 10,000, and that would be 7,000. So you can see here, as soon as n starts getting large, this middle term is going to dominate. So essentially, what we've got is an n log n algorithm. Tom?
I'm just curious, what base for the log do we default to for?
The answer is, that's a really good question. And the answer is kind of fun. remember that we don't care about small numbers. So we didn't care about the 7. And when you're doing logarithms, remember you can always convert between bases. And the way you convert by bases is by applying a fixed constant that scales the logarithm between the bases. And so we don't really care what base logarithm it is, because you can always convert between them. Now, obviously, if you're converting between a stupendously large base and a stupendously tiny base, then you are kind of like fudging and futzing a bit too much. But for the most part, for small constants, we don't care, as long as you're not doing anything weird and silly. Okay, so this takes us to, oh, this laptop is getting sleepy. Actually, I've got some good news. Do people want a surprise? It finished! Yeah, we can give a round of applause to the algorithm. But now we have a new find repeats that we can run. Find repeats 3, which uses the new method we've just discovered with the suffix array. So let's give that a run. And what I'm going to do is I'm going to add the time command and add this, which will allow us to see how long it takes if we don't get it to produce all those lines of output that we have to scroll through. So find repeats 3 is taking 0.88 of a second to run. And let's run the exact same command with find repeats 2. Find repeats 2 takes 1.53 seconds. We run find repeats 1, and it's off doing its thing. So it does seem like we did get a real advantage from using our suffix array and creating a faster version of this algorithm. We can also see that in the difference between our theoretical time analysis, which went from n squared m, where we were really using that m all the time, to n squared m, where we got some savings because on average we weren't actually going to do that many character comparisons for each of the inner loops, to our new suffix array one, where we now have logarithmic time. So this is a real improvement, and you can see it up there in the fact that our version 0 is still going forever, or our version 1 is still going forever, and our version 1 was multiple hundreds of times faster, and then our version 2, or version 3, sorry, version 1, 2, and 3. Version 1 is the naive version, version 2 is where we had the average case improvement, and then our number 3 was where we used the suffix array, and it doubled in speed again. So there are a few downsides to our number 3. Number 3 now stores these big tables instead of just going through bit by bit. So it does use a bit of disk space. This gives us that space-time trade-off that we were talking about. It also is a little more complicated. The actual code takes up more space, even in pseudocode. And if you look at the actual implementation that I wrote, so there's our time, and you'll notice here that I've added a factor of m out the front, and this is because we're actually sorting strings, and sorting strings takes a bit more time because you have to actually look through the individual letters of the strings. It's not the same as sorting an item where you can immediately tell at the first letter how to sort, but we'll go through more of that later. So let's do another version of our computation about how long does it take to run. So going by the speed of my MacBook, 10 to the 10 operations per second. For n is 1,000,000, m is 100. If we compute m log n, this gives us 4 times 10 to the 9. Just feed that in. It's roughly 1 second, which is consistent with what we saw when we ran it on the actual computer. And let's run it on the actual computer and just produce that result again. It takes 0.9 of a second. So our desk estimate here is actually really accurate. And I'm always a little bit surprised when this happens because computers are complicated, but the fact that this does give us a reasonable sense of the accuracy, I think is really cool and interesting. So zooming out back to our bigger code cracking picture, here is the table of what we'd get with different parameters. So there's War and Peace with m equals 25, and then various different lengths of inputs. And you can see that very quickly version 0 not only becomes too slow such that it's annoying and we have to wait around, but it becomes so slow that it would take thousands of years for the algorithm to actually finish. And so this tells you the importance of what we're actually doing in the classroom here. If you don't pay close attention to your algorithms, you can end up with one which actually won't solve your problem in not only quick time, but in all the time you have available. But we can still do better. Otherwise, again, we could have ended class now, but still got a bit to go. So with a better string sorting algorithm, we can save some time on this k log k factor that we were talking about, because there are some special algorithms you can use for strings. So we could use something and get about a 50% speed up, which would then take about 50 seconds to sort 50 megabytes worth of strings. This is a few hours of programmer time, so I would have to go down and sit and spend quite a while writing this code to improve our suffix-array version. But that would be a nice improvement. We could then figure out a better way of generating the suffix-array rather than doing this kind of annoying two-column thing and then sorting. There are algorithms that Professor Alistair Moffat, who teaches the other semester, actually worked on to try and build suffix arrays faster. And if we use one of those algorithms, we can get a bit more of a speed up again. Perhaps we can halve the time once more. This is now a few days of programmer work, and we get a substantial improvement in algorithmic complexity from doing this. So that seems like a nice thing to do. So are we done? Do you think we've improved our algorithm enough? Annie's shaking her head. Nah, there's still more to go. So we can still do better. One thing we could try, we could, instead of writing programs in Python or C, we could try writing assembly code. And maybe we'd get a little bit of a speed up there. I mean, compilers, the programs that convert the code that you write into code that the computer runs, they're pretty good these days. So I don't know how much more improvement we'll get from that, but maybe a little. But we can still do better. Does anyone have an idea? Okay, we've tried all these things. We've improved our algorithm. What can we do now? Are we totally stuck? What would I find if I opened up my MacBook? This is an expensive MacBook. What's in there? Who said that? Tom. Yeah, multiple cores. So inside this MacBook, I think there are 16 cores. And each of those cores is, in a sense, its own computer. So if I could find some way of splitting up this work of finding repeats into smaller chunks, then maybe I could take advantage of the fact that my computer can actually do multiple things at once, because there are multiple machines inside of it all running simultaneously. And this is actually, if you take a scan of an Intel processor, this is more or less what it looks like inside. You can see that the same structures are replicated over and over again. And these are the multiple cores, multiple independent processing units inside a modern chip. But we have a problem. What's the problem that we have? I want to use my algorithm for finding repeated substrings, and I have lots of cores, but do you have a guess? What's the problem?
System error.
System error? Well, it wouldn't be, given that the code works, probably wouldn't get an error, but how do you split things up? Do you know how to split things up? No, right? I don't know how to split things up, obviously, either. The algorithm that we've written doesn't split. Like, if we ran our algorithm on all the different cores, all we'd get is the same answer 16 times, which doesn't actually give us an improvement. So in order to take advantage of this, we have to come up with a new algorithm that somehow has a good way of getting the same correct answer, but in a way that splits up the work between the different cores. So this is another way of saying that our algorithm doesn't parallelize. There's a big takeaway from all of this, which is that problems can be solved at multiple different levels. We did a whole bunch of different sorts of techniques to try and solve the problem. We did analysis on a theoretical sense, we did it on an empirical sense, and we did it on we did it both average case and worst case. And beyond that, we tried all different kinds of methods for improvements. We tried small algorithmic improvements, we tried adding a data structure, And then the one that didn't work today was trying to take advantage of the actual architecture of the particular machines that we were running on, knowing that we had multiple cores available. And all of these different things are the types of techniques that you learn through this process of algorithmic analysis, and that is what our class is really about. It's also what makes computer science fun. There are lots of different ways to make things better. You can spend time hacking away at that little bit of assembly code, or you could spend your days trying to figure out the theoretical properties and trying to come up with new potential arrangements of things. And this is actually quite an enjoyable activity. Some people really like writing code and tuning the code. Some people enjoy thinking about the mathematical structures. Other people enjoy tinkering with the designs of hardware to make a faster chip that will take better advantage of the types of algorithms that we can use. And all of these different things together are what make computer science and what allowed us to defeat the Nazis.
I'm designing a machine that will allow us to break every message, every day, instantly. I'm just a mathematician.
Sometimes it is the people who no one imagines anything of who do the things that no one can imagine.
And I would like to say that at the end of this course, all of you will be equipped to be Benedict Cumberbatch. I hope. But if not, at least you'll, I highly encourage you to go back and watch that movie, which I've suddenly forgotten the title. Anyone remember the name? The Imitation Game, that's right. The Imitation Game, which is somewhat fictionalized. There are some issues with it, but it still is a really nice retelling of some of this story around the life of Alan Turing, who we will discuss later in the class, who came up with some of the important concepts both in theoretical computer science, but also who helped develop these computers that cracked the Enigma code. And so hopefully today you've had a little bit of that fun preview into that. Also, you will have seen at the end of that clip, there were some of these like spinning machines that seemed to be like rolling, like old cinema cameras that had tapes rolling around. Those weren't cameras. That's what old computers used to look like. They had actual magnetic tape that had to be fed through, and that it would write the answers onto the tape. Okay, so this chapter is called Making Algorithms in the Real World. And here we're going to talk about some more spiritually kind of things about the nature of the universe, as well as some very practical things about how to actually get started writing your own programs and implementing algorithms on a computer. And for this semester, we're going to implement our algorithms in the C programming language, which was created in roughly 1969, with early versions coming out over a few years subsequent. Now, the C programming language is what we called a compiled programming language, which essentially means that when you write the code, before actually running it, you have to give your code to a second program called a compiler. This program will convert it into something that your operating system can then send to the chips on your computer to run directly. And so one of the early steps that you'll need to get used to doing is running this conversion program, this compiler, to convert the C code that you've written into the code that will actually run. Now, the people who wrote the specification for the C language, and one of the early books, were Brian Kernighan and Dennis Ritchie. Now, as much as Brian Kernighan will deny that he created the C language, he was a key figure in its popularization and development, and wrote many of the early programs. And in fact, rather than me telling you about him, I think we're better off hearing it from the man himself.
Hi to all the students in Foundations of Algorithms at the University of Melbourne. I'm Brian Kernighan. I teach computer science at Princeton University in the United States. I wrote the first book on C along with Dennis Ritchie, and I helped build some of the early Unix tools like the ARC programming language. I hope you're all enjoying learning everything there is to know about algorithms. Good luck with the rest of your semester.
So that was really him. That was not an AI version. And very grateful to hear from a few of our friends overseas who've actually been instrumental in making some of this stuff. And this is another reason why computer science is kind of cool, because a lot of the people who invented this stuff are still alive and around. And if you travel to the United States one day, you can knock on Brian Kernighan's door and say like, I saw you in my lecture in Australia and we learned from your textbook. Okay, it is time to see our very first C program. So let's open up my computer in Visual Studio Code again. So the first thing that we're going to do is we're going to create a new file and save it, and I'm going to call this Hello World. And now I'm going to type in what will start off as actually looking like some fairly mysterious syntax. And as we go through semester, hopefully by week 4, you'll actually understand all the different components of what we're writing here. So I'm going to start with the following. See. So this is the complete Hello World program. This is what you need to write in the C programming language in order to print the words Hello World to the screen. And let's run that and see if it works. Now, I'm going to try and split the screen, so do that. Now, the first thing that I have to do is run my program. Is that right? Do I run my program straight away? What did I say about the C programming language, KJ? Say a bit louder. I need to compile my program. What this means, again, remember, is to take the thing that looks kind of like English E, it's not quite English, but looks English E, and convert that to instructions that the computer can actually send to the processor. And so my personal preference is to use a compiler called Clang, but there's also a compiler called GCC that a lot of people like to use, and there's been a big fight historically over which one is better. It changes all the time. My preference is Clang, try them both. So the way we use it is we type in the command into the terminal, Clang, or GCC if you want to use GCC. Let's type in Clang, and then the name of the program that we want to compile. So in this case, I've called my file helloworld.c, and so I will tell that to Clang. I'll press enter. I press enter, nothing happens. No? No suggestions? Tom, you already know. Okay, KJ, this is the last one for now. Tell me what's going wrong.
Right now you've just said that this is a program that exists in this place, but you haven't sort of given the instructions that it needs to output, I suppose, at this moment.
What do you think it's done?
I think it's just like pulled the place where the code is written, I suppose. Maybe that's what you're working for.
But in terms of what my computer has actually done, remember what a compiler's purpose is. The purpose of the compiler is to take some code and convert it. And if I look, let me look at what's actually inside my current directory. I'm going to compile or run Clang on helloworld.c. Now let's look at my directory. There's a new file in there, a.out. So KJ, has my compiler done this conversion process? Yeah, it's converted my program into this program a.out, but now we have to actually run it. And so what I can do is I can type the following command, // and then this tells the computer, look in the current directory, and then look inside the current directory. That's the slash. Dot means current directory and slash means inside of. So inside of the current directory, there's a program called a.out, and run that. Oh, there we go. Hello world. And now I've done some other funny things here, like there are all a bunch of symbols that were unclear about what they do. For now, I'm only going to tell you what one of them does, and this is the /n. So somehow we have to tell the computer how to put a new line in. And if we wrote the word new line, what's that going to do? Oh, did I not save it? Hello world. Let's compile that. hello world new line. So that doesn't work. So we need some way to tell the computer that we want it to produce a new line and not say the words new line. And so the way we do that is with this \n here. Now, because all of you have some programming experience before, I'm not going to do a full detailed breakdown of all of these lines right now. But I will tell you that the printf function is going to be one of the key things that you'll need to use over the next few weeks, learning how to produce output from your program, and then pretty soon we're going to learn how to take input into your program. So printf and one of its partner functions, scanf, are going to be two of the functions that will start off learning to how to do this. So this is all a little odd because at the end of the day, hello world.c is just a text file. I may have put a .c at the end, but when I opened it up, it was just words. And so this is where the compiler really becomes important because it's the thing that converts those words into actual instructions for the computer. And what was actually happening behind the scenes is I was using a second program called a shell to give me a place to type in commands into. So it's programs built on top of programs, built on top of programs, built on top of programs, which is also why I thought the Ninja Turtles would be an appropriate metaphor here, because of, if any of you know the metaphor of the turtles standing on the turtles, standing on the turtles, it's turtles all the way down. It's programs built on programs built on programs. If you want to run a program, you have to use a program to compile your program. In order to instruct the computer to compile the program, you have to enter a command into another program to tell the compiler program to compile your program, etc., etc. So you get lost in this very quickly, but it's also part of the beauty here is that there's really nice, complex structure to appreciate. So why couldn't I run just the command hello world? Why didn't that work? Guys, you've been in the class before. Here, pass the microphone. Why couldn't I just run the command hello world?
Because the computer wouldn't know what to do with that.
Yeah, what is hello world? Hello world isn't a program yet. I mean, we're trying to print a string called hello world, but it's not there. What was our program called?
Hello world.c.
Well, that wasn't the program itself. Those were the code that we can then give to the compiler to make the program, right? So the question is what actually is the program? One way of thinking about it is the program is the set of instructions that you can then feed to a compiler. And another way of saying it is it's the thing that comes out of the compiler. So what was the thing that came out of the compiler called? a.out. So what we can actually do is we can tell the compiler, hey, a.out is not a very descriptive name. Let's call it something slightly more descriptive. So I'm going to run clang hello world.c, only this time I'm going to tell the compiler something additional. I'm going to give it what we call a flag, which in this case is represented with a dash, and then a letter that indicates which of the flags we want. This is the output flag, which is specific to certain programs, but for programs that support it, tells it when you produce output, give it this name. And so what would make more sense, Jen, for a name for our program? Well, if I call it to say hello world, that's a bit much. So what should I call it? Just hello world sounds good. And now if I look in my directory over there, I have a new file called hello world. And if I click on it, it says this file is either binary or uses an unsupported text encoding. Why is it giving me this message? What's inside that file?
Zeros and ones.
In a way, but all files are zeros and ones. But what do the zeros and ones represent in this file?
The compiled version?
Yeah, that's the compiled version. So this is the result of giving our C instructions to the compiler. And I will actually show you for a second what this looks like. So, So this is what it would look like if I opened up those zeros and ones in base 16. So if I looked at all the zeros and ones in the program and then converted those zeros and ones into base 16, this is what it would look like. It's not very easy to read. There's another program on the computer that I can feed it to. And then this, what it will actually do is it will interpret the zeros and ones and tell me what the assembly instructions are that those zeros and ones actually mean, that they correspond to. Because at the end of the day, what happens inside the computer is whatever the numbers are that you've produced through the compiler, those get fed as electrical signals down the wires to the computer, to the actual central processing unit, which is a chip inside, and then based on which wires are electrically active and which ones are not electrically active, it knows what instructions to do and what data to get. And so what this program is showing is how that conversion works between those zeros and ones that correspond to which wires are active or not, and the actual assembly instructions or machine code instructions. And if you're in the more comfortable class, they'll probably have a fair bit of a discussion about how this whole process works. But for now, you can have seen this once and never have to think about it probably for the next 3 years. Although I think it's cool. So now we still have a problem. I'm going to type in hello world. Still doesn't work. Command not found, hello world. Jen, what's going wrong?
I'm not really sure, to be honest.
Okay, do you remember what I had to do to run a.out?
No.
Here, I'll jog your memory a little bit. What did I do to run a.out that I haven't done for hello world? Yeah, I need that /. And what's actually happening here is the computer has a list of places that it knows where to find programs. So it's got a directory, like, for example, one might be called bin, and it always looks inside bin every time you give it the name of a command you want to run. And hello world, this program that we've just made, isn't inside bin, and so it doesn't know where to look. And so what we're going to tell it is we're going to tell it, look inside the current directory. So dot means current directory, and / means inside. So if we look inside our current directory, so let's replace this with hello world. Okay, now we're ready for our next program, which is just looking at very basic input and output. So we know how to put things out. Now we want to figure out how to get some things in. And this is where we're going to see the partner to printf scanf. And I'm going to go through this pretty quickly because you've had some programming experience, because chatbots now exist that can give you more syntax. And so we're not going to spend as much time on syntax this year. And then we're going to focus a little more on the actual algorithmic side. So this is io.c. So first thing, I'm going to create actually, teaching moment. See that white dot in VS Code? That means my file is not saved. If you try and compile this, you will compile the version that you last saved and not this version. One of the things I see with students getting confused the most with using VS Code is that white dot will still be there. They're compiling the old version. They're like, why didn't it work? I just changed this thing, only to realize that they haven't saved. Anyway, time for a new file, and we're going to call this one io.c. Is that coming up? Yes. And so I'm going to include the same thing that I did before. And for now, we just have this mysterious syntax. Okay, now what I'm doing here is I am declaring to the compiler that I want to create an integer. An integer is just C's way of saying a number, and depending on the computer, the number is going to be allowed to be of different sizes. And we'll talk a bit more about what that means in a few minutes, but for now, it's just a number. Now, it's not any old number, it's a number, it's a whole number, a formal integer, just like the way we talk about it in mathematics. We also have other types in C. Let's say a double, I'll make the integer I and the double D. And a double, that's where we can have numbers with a decimal point in them. And I'm going to have a char, C, a character. And what I'm going to do is I'm going to ask the user to enter in values for all of these and then just print them out. Very simple program. And for this, I'm going to use the partner function to printf called scanf. And the F here stands for formatted because it allows us to very easily tell the computer read in whatever the user is doing and interpret it in this way, or read in the instructions that I've given you and interpret it in a way that you can format it properly. So in order for these functions to work, they take in some input in the form of a string, and the way we represent a string in C is with these double quotes. And this is what we call a format string. It tells the computer what format to put things into or to expect them to come in. And so in this case, if I want to read in an integer, I'm going to use a format specifier inside my format string. And a format specifier is just a fancy way of saying, we've agreed that when you write the percentage sign and the letter D, that is going to tell scanf that you're expecting an integer. So in this case, my format string is %d. The %d is also the format specifier for an integer. And I am going to give my function as well where I want it to put the integer when I'm done. And for now, I'm not going to explain why. But for integers and doubles and characters, we're going to have to add a percentage sign before the name of the variable that we want to put it into. So I want to put what the user types in into the integer I. The next thing that the user puts in, I want the computer to put it into the double. And then the next thing, I want it to put into the character. Okay, already I've made a mistake. Can anyone see what mistake I've made? Sorry, Oscar. Yes, what was your name?
Josh.
Josh.
You haven't changed the format. What's it called?
Format specifier. So right now, my format specifier for all three of them is the integer format specifier. But the second thing that I've asked for is a double, and the third thing that I've asked for is a character. So you can look up in the manual, and I will show. Oh. You can actually look up inside the computer's manual what is the right format specifier for what type of thing. And so this is an old piece of internet slang. How many of you have seen RTFM before? This is more like 1990s internet slang, but it stands for read the effing manual. And in this case, that holds true as well. So I'm going to open up my terminal, and I'm going to type in the command man, which is short for manual, and I'm going to type in scanf. And then let's open this up big. And this is what is called the man pages. And here is a full description of all the different things that you can do with scanf. And this gets very long. But if we scroll down, we can see all the different format specifiers. See, here we go, %d matches an optionally signed decimal integer, etc., etc. So if you wanted to, you could go through and read the manual and learn about the different functions that way. That's an important technique. The other thing for this class you can do is CS50, the class at Harvard that I mentioned, has a boiled down version of the manual pages for all the functions that we use in class that writes it in much simpler English and that's much more accessible, because these man pages are the full man pages. So while you want to graduate to reading the full ones, it's okay to read the simplified ones for now. And then on top of that, a lot of programmers will use sites like Stack Overflow or tools like large language models to ask queries more directly rather than reading through the manual. These tools are not very good at replacing the man pages, but they're useful as a way of augmenting it. So let's go back to io.c and change my format specifiers. And if we'd been paying attention, we would have seen that an F would work for my floating point number because there's a decimal point in it, and a C would work for my character. You'll also notice that in the C programming language, I'm required to put a semicolon at the end of every line. This is because when the compilers were designed in the late 1960s and the 1970s, it was a little trickier to figure out the right way to teach a compiler how to understand like a sentence's worth of code, and a semicolon or an indicator like that made it quite easy to do. So that's why we have the semicolon. So let's go inside lecture 1, let's go inside live. Just like Jen suggested, I'm going to run my compiler with io.c, but give it the O flag so that I can give it a reasonable name. And now you'll see I actually have a couple of warnings to deal with. And this is a normal thing, and this is a good thing. But you generally want to read the warnings because they'll tell you maybe you're doing something a little fishy with your code. So the first thing is this warning here. Warning, format specifies float star, but the argument has the type double star. So if we look what I've done here, I've used a double and it's saying double, but you used an F, and an F is for a float. So you've done something wrong there. Actually, this probably will work fine. But if we're following the advice of the compiler in this case, it says, you know, there should be an LF. An LF actually means a long float. A double is twice as long as a normal floating point number, so it's better at representing decimal numbers. So I've used that here because we're going to use doubles for our semester rather than floats. Floats do get used in a couple of places now that AI is around, but for a long time I was saying, you know, whenever you need a number with a decimal point, just use a double because it's more accurate and it has more space in it. So we're going to follow the advice of the compiler and put an L in there. And then it also tells me that I've forgotten to write a name for that variable there. Oh, there. And don't worry about what in particular that means for the time being. So let's go ahead and compile IO. And now we'll see in the side we have IO there. But if I run IO, it's not doing anything. Jen, there you are. What's going on?
I don't know.
So what are the commands? What are the three commands that I've told my computer to do?
To store the input in the address.
So I've asked it to get input from the user and store it in three variables. Jen, what's my mistake then? I'm the user. The program is asking for input. What have I done? I haven't put input in. So let's give it some input. 5 and then 55 and then 5.5, and it just finishes.
You didn't print it?
I didn't print it. I didn't ask it to actually do anything with it. So now let's do printf, and I'm going to the integer was the float was, or the double, I should say. The double was the char and you can see with the syntax here, I'm using format specifiers again in the printf string. And what this means is I also have to tell it what is D, L, F, and C going to refer to. And so I provide these as additional arguments to the function here. So that's going to be I, D, and C. And at the end of this line of the format string, I'm going to remember a /n so that it prints a new line at the end, so it just looks pretty. And then at the end of the whole line, what am I missing? Semicolon. Okay, so put my semicolon in. And also, if I'm being nice, I'd probably tell the user, please enter an int here. And then what should I do over on this line? What should I write? Jen? So I just did please enter an int. What am I missing on this line then?
Please enter a like decimal.
Yeah, please enter a decimal or a double. And then please enter a...
Is that like a word or something?
That's a character. But excellent. Okay, and now let's run it. Please enter an int. Please enter a double. Ooh, what's going on?
If I'd been reading the man pages carefully, I would have seen that ordinarily what happens is the format specifiers will automatically handle the spaces to some extent. This is not true for the character format specifier because you can use the %c specifier to actually read a space itself. So what we need to do in order to get scanf to eat up the spaces is actually to put a space before the %c sign. One other thing I'll note here is you will see that I put ampersands before a bunch of the variable names in scanf. Now, this is something that we'll have to explain a little later in semester, but for now, just take note of it. Normally, we write variable names without the ampersand sign, but now, for scanf, we're putting it there.
So the next thing we need to do is, now that we actually have our have some numbers that we've been able to read in, we now need to be able to do some operations with them. Now, C supports a whole variety of operations, many, 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 but for our class, we're going to focus for now on a limited set of them. So we're going to focus only on these ones. So plus, minus, multiplication, division, division in a modular sense, and we'll talk about what that is in a little, as well as checking for equality, checking for greater than, checking for less than, and also checking for non-equality. But to do all of these things, we're firstly going to have to understand a little bit more about how C handles different types of variables. Now, we've already seen 3 different types of variables, or at least 2, and then one which I couldn't figure out how to get working. And so let's talk a bit about the types that C supports. So the first thing that we should think about is how to represent a single character, a single letter in C. And to do this, we're going to use a system called the American Standard Code for Information Interchange, or ASCII, if you read the letters off. And so if any of you have seen ASCII art, this is what it's actually standing for: a series of roughly 127 characters that can be represented in a very small number. And in C, the type that we're going to use, the type of variable that can hold a single character, is called HR, short for character. And this is the complete chart of the mapping between numbers that are stored inside your computer in binary or in hex or in whatever, and the ASCII character that they represent. So what is number 65? A. Uppercase A, correct, uppercase A. And so we can see that our uppercase numbers start at 65 and go to 90, and then our lowercase numbers start at 97 and go to 122. So if you ever have wondered, well, how does a computer know what letters are? Well, really the answer is it doesn't really know what letters are. What it's doing behind the scenes is it's storing a number, and then somewhere in a file on the computer, there's like, when you see this number, print this pattern of dots to the screen. And for example, if the number is 65, the pattern of dots is instructed to look like the letter A. It doesn't have a deeper understanding of what the letter is, other than things around what number should produce what shape, and how should that shape relate to shapes around it. Yes?
Do the characters in the first 2 rows also count as characters in C?
Yes. All of these are valid characters in C, but some of them are what we call non-printable characters. That means if you use them and you try and print them, they won't show up. So for example, a new line character is an example of a special character, and a null character is an example of a non-printable character. You have more question? Okay, so that seems easy enough. Characters, so put in a number, you get a given character. You can do all kinds of fun things with the fact that you know that under the hood, these letters are really just numbers. So you can do addition and subtraction with letters, just like you would do with numbers. So for example, if you compute the difference between uppercase A and lowercase a and add that to lowercase b, then you can get to uppercase B, then you can convert that to lowercase b just by using the fact that you know the size of the gap between the uppercase letters and the lowercase letters. And we'll have you do some of that in the exercises. Okay, that's good, but let's do a bit of maths. So here is a clock that I was looking at this morning, and it was 9 a.m. and I wanted to know what 9 plus 4 was. What's 9 plus 4? Come on, guys. What year are you in? What's 9 plus 4? That's wrong. 9, 10, 11, 12, 1. You guys are wrong. Okay, what's 9 plus 5?
2.
Okay, 9 plus 6?
3.
9 plus 7? What about 9 times 2?
6.
Okay, so now we've entered a realm of a different type of number. And actually, in mathematics, if you take maths at uni, you'll start to learn about different number systems and not just the plain integers that we're used to. So what is actually happening here is an example of what we call modular arithmetic. This is where you have only a fixed number of numbers in your group before they kind of wrap around again. And we're all used to doing this from the clocks that we use. So even though it seems like a bit of a new idea, you're actually quite familiar with it already. And in fact, our computers behind the scenes often use something like this because we've only got so many slots on switches inside the computer to turn it on and off. So let me get my board out again. And my pen, wherever it went. Here we are. So let's imagine we have 2 switches. It's like these are light switches. How many different combinations are there of arranging the light switches in on and off combinations? 4. So we have 4 different combinations, and so let's say we can go off, 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 on, what's next? On, off, and then on. And so this is combination, what number? 0. Combination 1, 2, 3. So this seems like a reasonable way of representing integers in our system. But then if I only have 2 switches, when I get to the end, well, I guess I can go back to off again. That's the next kind of thing. That's the next kind of arrangement in my cycle. And so this is what C is going to do with numbers. When you run out of room in the integer that you created, when you create an integer, it sets aside a number of bits, which are just like switches. And when you have all of the switches on, and then you add another one to it, it's going to flip them all off again. And so this is just like our clock here, where we wrap around once we get to the end, except instead of having our number 12 at the top, we're going to use that as our number 0. So when all the switches are off, that'll be 0, and when all the switches are on, that'll be our maximum number. So this is kind of getting to the limits of how high a computer can really count. So if we're arranging our clock like the bits in a 32-bit computer, which were probably the computers that your parents grew up with, or not grew up with, but used in their earlier careers, and that I certainly grew up with, we have 32 switches that are allocated for a given number. So what happens when we've turned all our 32 switches on? What number is that in this arrangement? There's a big hint on the board. Okay, so if we have 2 switches, how many combinations? 2 squared. If we have 3 switches, 2 to the 3. If we have 4 switches, so you see the pattern. But remember, we save one of the switch combinations to represent 0. So what's the largest number that we can represent with 32 switches? 2 to the 32 minus 1, because that minus 1 accounts for that 0 there. And so that's what's happening here. And now, just like I had with the normal representation of the numbers, we could just write this out in binary with a 1 representing a switch that's on and a 0 representing a switch that is off. Now, this is all well and good, but we've only got positive numbers. So what should I do to represent negative numbers? Annie, Tom, and Oscar, I've heard a lot from you guys. Yes, what's your name? Vimal. Vimal? Yeah.
You can use a bit at the start and like make that a 1 or 0 to represent negatives.
Oh, you already know the answer. So there are a few things that we can do. One really nice, obvious way of doing it is split the numbers that we have in half and use all the numbers that start with a 1, which is halfway through, use them as our negative numbers. And so we'll talk a little bit more about how this representation works in detail later in semester. But what we've actually done here is kind of clever and tricky, and we'll explain why we've done it later. But we're actually doing it such that deviations from that 0 in either direction increase the magnitude of the number, whereas the sign is determined by that largest bit, that 1. So if you go from 0, and then that direction is 1, that direction is -1, you go another one along, you go 2, -2, 3, -3, etc., etc. So now the issue we have is that, so we've got 32 switches, but 2 to the 32, anyone know off the top of their head roughly what it is? 4.2 billion. Good, Tom. And 4.2 billion seems big, but like I have more than $4.2 billion in my bank account. So I need a bigger number if I'm going to represent how rich I am. This is how you know that I really love teaching this class, because I have as much money as Jeff Bezos, and yet this is where I want to be. So one solution could be, well, just add more switches, add more bits. Well, what that means is redesigning a new computer chip that has 64 wires coming in instead of 32. Why 64? Well, that's doubling, and we like doubling in computer science because powers of 2 are very easy to work with from the perspective of actually doing the design of the chips. So let's add 64 bits. What's 2 to the 64? 1.8 times 10 to the 19. Now, are there things that we might want to represent that are larger than 10 to the 19? Number of atoms in the universe we probably want to have a way to write down, but we likely don't need to count through all of them. But there are definitely instances where we do want more than 1 times 10 to the 19. Well, so what's our next step? If one integer of 64 bits isn't large enough, what can we do? KJ?
Start representing things in a different form. Like we have, what was it, 1.8 into 10 to the 19.
So that's a really nice idea. First time I've heard that ever in 5 years of teaching the class. Great idea. We could represent numbers differently. Another idea. Yeah.
Maybe we use 2 machines simultaneously. We use 2 machines simultaneously.
2 machines simultaneously? Well, does my machine only have room for 1 integer in it? How many integers do you think I can fit? 2? 12?
I have no idea.
There are more than 64 switches inside my computer, let me tell you. But that's the right idea. Instead of using multiple computers, instead we can use multiple sets of switches. So multiple integers, combine them together, and have a nice way of using this representation to actually represent larger and larger numbers. And we can do the same thing where we represent like 2 to the 32 minus 1 or 2 to the 64 minus 1. Do the same thing with negative numbers. And we'd hope that C would be smart enough to deal with this. But unfortunately not. The C specification provides very few guarantees about the size of numbers and their relative sizes. And you're actually going to have to use various tricks and various extensions that allow you to actually check what is the maximum represented size of the number available. C is going to guarantee at least this minimal size of the numbers available, but determining the additional ones will require you to dig into the code a little more. So, in the last 3 minutes of class, I want to show you something pretty cool. So let's ask the question, okay, we know about integer representation now. To how many decimal places can a computer represent a floating point number or a number with a decimal point? Can we represent every possible decimal number in the world on an actual computer? Annie shakes her head, says no. Why do you say no? See you, Tom. Pass that to Annie quickly.
Like computer represent floating point numbers with like fractions like 2 to the negative powers, and like you can't represent like every decimal
But that's a concrete thing. You're giving me how computers do represent them, not how they possibly could. So let's imagine I pick a random decimal number out of all the decimal numbers in the world. How many digits does it have? Infinite. And does my computer have infinite switches in it? No. So now we've got a problem, is that there are numbers that we want to represent that our computer doesn't actually have the switches for. And this is where I think computer science gets really, really interesting, because it starts to interplay with the actual nature of our universe. Not only does our computer only have a set number of switches inside it, but there are only a certain number of switches in the entire universe. Like, imagine we took every atom and turned that atom into a switch for our like giant universe computer. We still wouldn't be able to represent even one full decimal number. I mean, we could use it, we could do fractions, but if we were truly picking a number that went out to infinity, we've got no way to represent that in a computer, even the size of the universe. And this is where I think there are some really interesting directions in computer science and some wonderful research papers that talk about the ultimate limits of computation, not just about the limits of the computation that you can do on a laptop, but what if we turned the entire universe into a computer? What kind of algorithms would be possible? What kind of problems remain outside the scope of anyone in the universe ever being able to do this, or outside of any universe? Or what happens if we allow time travel? Are there still problems that time travelers couldn't do now that they have infinite time? And the answer in all of these cases is amazingly yes. There are problems that are largely outside the scope of all reasonable models of computation. And with that, I will leave you to have a brief think about our place in the universe and how we're these little small creatures running our small computations, but also the power of what algorithmic analysis allows us to do, and the way it allows us to grapple not just with the interesting questions about how do we crack codes, defeat the Nazis, and do interesting things on our computer, but it answers questions and gives us new questions about our place in the universe. Thank you very much. I will see you all next week.